Okay, I've got a 50-pound iron object. It's got a specific heat given here, and it's at 700 degrees Fahrenheit. Throw it into a tank with 2,121 pounds of oil with a specific heat given there. It's initially at 80 degrees Fahrenheit. I want to first find the equilibrium temperature and then the entropy production. Now, this is an isolated system. Okay, so the total energy has to remain zero, right? There's no heat loss or work being done, okay, because I'm going to take the object and this huge amount of oil as a system where it's kind of an isolated system. Therefore, the change in energy of the isolated system equals the change in energy of the oil plus the change in energy of the iron, which is going to equal zero, okay, because there's no heat and no work done to the surroundings, right? I'm kind of including the oil as the surroundings into the entire system. So really what this boils down to is the mass times C times delta T of the oil plus the mass times C times delta T of the iron equals zero. And again, I use this because these are incompressible substances. We've got a liquid and a solid. We don't have tables for them, so we're going to use specific heat in order to calculate this. Okay, so I take I guess I have the oil first, so that's 2,021 pounds times C, which is 0.45 BTUs per pound, times the temperature change. Now the temperature change is final minus initial, which is going to be T final minus T initial. And because I'm using difference in temperature, I can just stay with Fahrenheit here. I don't need to go to Rankine because I don't need the absolute temperature. I'm only really looking at the change in temperature. So moving on to iron, I have 50 pounds of iron, C of 0.1, and my temperature change here is the final temperature minus the initial temperature was 700. And again, these two things have to add together and equal zero, which gives me a final temperature of actually, I wonder if I need to... No, I think I'm okay. 83 degrees Fahrenheit. Okay, now that I have that, I'm going to go ahead and find the entropy production, which is the same idea, that sigma equals delta S of the oil plus delta S of the iron. So one's going to increase, one's going to decrease in entropy, but the total value has to come out to sigma. And again, this is true because there's no heat transfer to the surroundings. Essentially, I've included the oil, the surroundings in this. So for the isolated system, the sigma is the change in entropy of the oil plus the change in entropy of the iron, which is MC times the natural log of T final over T initial. This would be oil plus MC natural log T final over T initial for the iron. Now, since I'm doing ratios here, I am going to have to use absolute temperatures. So just be careful with that. So I start with the oil. I have 2121 times 0.45. And again, I'm using specific heat because this is incompressible substance. I don't have tables for it. So T final, that is going to be 543, 460 plus that, divided by the initial. This is for the oil, which is 80, which is going to be, 540. Plus, that'll be the mass of the iron, which is 50, times specific heat of the iron, which is 0.1, times the natural log, again, T final, which is going to be 543, divided by 1160, because it's 700 plus um, 460, 700 plus 460. Therefore, the total change, or the total entropy production, is 1.84 BTUs per degree Rankine. Again, that's positive. It has to be positive because there's always an increase in entropy. Okay, and that's because this is an isolated system, right? So there's no transfer with the surroundings. I'm including the surroundings in it. So sigma has to be positive in this sort of a system.